We have different types of data structures: arrays, queues, stacks, trees, graphs, and more. Understanding each of these structures can be a little bit overwhelming, but it's not impossible. In this video, I'm going to break down the 7 most important data structures, explain how they work, simplify each data structure, and highlight common use case for each of them. First of all, what are data structures and why should you care? Simply put, a data structure is a way of storing and organizing data in a way that it can be used efficiently. In this video, we will not be going deep into time complexity. There's a whole dedicated video for that. But let's start with the first data structures. Arrays. An array is a list of items. The items might be similar, they might be different depending on the programming language. They might be of the same data types or different data types. But regardless, each element in an array is assigned an index, that is a number that allows for quick access. So in JavaScript, for example, the first element in an array is assigned index 0, next element index 1, and progressively like that. Arrays are stored in contiguous memory, which means that each element are next to one another in memory. They are situated next to one another in memory. So if a new element is added in the middle of the array, the entire array will shift and adjust. The advantage of arrays is that it makes it easy to read elements. Reading of elements is O of 1 when you're using an array because you have the index, so it's easier to look something up. The disadvantage is that they are less efficient when it comes to inserting new elements or deleting existing elements. When it comes to inserting and deleting, that is O of n. Again, if you do not know about time, complexity, big O notation, there are dedicated videos on that on my channel. For example, here we have an array called fruits, and it holds 3 different fruits. In this example, we can access apple by referencing its position, which is index 0. So just by calling index 0, we get apple. So access is fast with array, you can easily read. But when it comes to inserting or deleting, it is slow because you would have to shift other elements to adjust things. Next up, we have linked list. It's a chain of nodes. A linked list is a collection of elements called nodes. Each node stores data, and it also stores a pointer or a reference to the next node. Unlike arrays, linked lists do not use contiguous memory. So elements in a linked list do not have to be stored next to each other. As far as one node has the pointer to another node, you're always going to find the next element wherever it is, because the previous element we have a pointer to tell you where the next element is. So because every element in a linked list or every node in a linked list has data and it also has a pointer to the next element, that kind of helps us solve the issue we have with inserting and deleting when it comes to arrays. So with linked lists, we are able to delete or insert easily. The advantage of this is that linked lists do not have indexes, as the elements are not stored beside each other. So this means if you're looking for an element, you have to go through the list from the beginning. For example, if you're looking for the, say, third element, you have to go to the first element, have it point to second element, and then get to second element and have it point to third element, as opposed to in the case of arrays, where we have indexes. So it's like a two-way street, right? Arrays are excellent at reading elements, but a bit slower at inserting and deleting. But linked lists, however, on the other hand, they are faster at inserting and deleting, but they can be slower when it comes to reading elements. So in the case of arrays, don't forget, reading is O of 1, is fast. Insert and delete is O of n, a bit slower. But with linked list, reading is O of n, slower, but inserting and deleting is O of 1, faster. Now, hash tables or hash maps. Now, remember how arrays are stored, and for each value there is an index that numbers it. Well, with hash map, it's kind of the same thing, but the difference is that with hash maps, we get to dictate the index. And the hash map doesn't call it an index, it is called a key. So in hash map, it is always considered key and value. As opposed to in arrays where we have index and value, in hash map we have key values, key value pairs. Another difference between array and hash map is that arrays are ordered, hash maps are not ordered. So a hash table or a hash map is a data structure that stores data in key value pairs, a key and a value. Key, for example, in this case, key is fruit, value is apple. Key is vehicle, value is car. Or for example, say we have a detail about a woman named Mary, so we can have it in a key value pair. Name is Mary, age is 25, and key profession is software developer. Key country is value Nigeria. Make sense? With HashMap, looks up or reading are super fast. Once you have your key, you get your value ASAP. You don't need to search all through the entire data. Just with your key, you can access your value. Another example is a dictionary. Once you type in a word, you get the definition of that word, right? So when it comes to HashMap, reading or looks up are O of 1. They're super fast. Next up, we have stacks, last in, first out, LIFO. The simple way to grab the meaning of stack is to think of a stack of pancake, or a stack of plates, or a stack of books. I'm going to use pancakes because obviously I love pancakes. So a stack is a data structure that follows the last in, first out principle. All things being equal, if you have a stack, you can add to the top and you remove from the top, right? The last one you add in is the first one that goes out, all things being equal, right? And that's why it's called the last in, first out data structure. Stacks have 3 common operations: push, pop, pick. Pushing is when you add a new element to the top of the stack. Popping is when you remove the element from the top of the stack. And don't forget, the topmost element is usually the last one that was added. So that's popping, removing the topmost element from the stack, while picking is taking a look at the element, the top element of the stack, picking. All of these operations are very, very fast, and that's why stacks are optimal for certain problems. In real life example that I can think of now is the undo feature in a text editor. If you're working in a text editor, you can do Ctrl Z, Ctrl Z, Ctrl Z. That takes it. The changes are kind of stored in a stack. That's why the most recent change is the one that gets undone first, right? Another example is the back button in a browser tab. So your recent pages on a browser tab are stored as stacks, and that's why when you back, it goes back to the last page you visited, right? So if I visited facebook.com and then I go to google.com and then I go to instagram.com and then I go to my website bemisola.com, if I go back, it takes me back to instagram.com, which is the most recent that I visited, right? That's a real life example of stack, last in, first out. So stacks are great for things like depth first search or backtracking algorithm. If you need to backtrack, perfect. Queues, first in, first out. FIVO, first in, first out. Queues are a literal opposite of stacks. A queue works like a queue, like a literal queue. A queue at a restaurant, a queue at a bank. In this case, the first person to get into the line gets attended to first. If you get to a bank, you go on a queue. The sooner you get on the queue, the faster you get attended to. If you're the first person to get on the queue, you're going to be the first person to be attended to. If you're the last person to get on the queue, you're going to be the last person to be attended to. So it's a first out data structure. Queues have very similar operations to Stack. They also have 3 main operations. Remember, in Stack we have push, pop, pick. But here we have enqueue, dequeue, and front. Enqueue is just like push for stacks. Enqueue occurs when a new element is added to the back of the queue, while dequeue occurs when if an element is removed from the front of the queue. Why front is just like pick. It is when you take a look at the frontmost element in the queue. And just like in stacks, all of these operations are fast. O of 1, they are fast. I think in real world programming, queues are used a bit more frequently than stacks. Think of YouTube playlists. When you start watching a playlist, you need to start with the video or the song that was added first, and then you keep going on till you get to the video that was added last. So first in, first out. So queues are great for algorithm situations like managing requests in a server or processing tasks in order of their submission. Now, next up, we have trees. Just like the name says, it's literally like a tree. Trees have nodes, and the nodes are connected by edges in some form of hierarchy, like a family tree, great grandfather, grandmother, grandfather, father, mother, then grandchildren, like a form of hierarchy. The root node is usually at the top, and each node can then have child nodes, like a literal tree. The most common type of tree is the binary tree. It's very, very popular, where each node has at most 2 children. It is efficient for searching, inserting, deleting. When balanced, it uses the O of log n time complexity. For example, a very common example is like a family tree, where each person has parents and children. And a real life example that is also common is like a file system on a computer, where you have folders that contain subfolders, and those subfolders contain maybe another set of subfolders, and that one might contain files eventually. So trees are good for organizing things in hierarchy. The downside is that searching for something in a tree can take time if the element is like deep down the tree. Lastly, we have graphs. Like trees, graphs are made up of nodes and edges, and even trees and linked lists can be considered a type of graph. Graphs are used to represent relationships between different entities, how things connect. For example, how cities connect to each other by road, how people connect to each other on social media. Graphs can be directed one-way connection or undirected two-way connections, and some graphs can even be cyclic, where the two nodes point to each other. The edges between graphs can also be weighted, where the path, the edge, would also have a value associated to it. Graphs can be a bit complicated, and that's why so many people consider it one of the hardest to learn. Personally, for me, it's a bit hard to understand, but maybe I'll just make a dedicated video on graphs because there's a whole lot about graphs. Let's think of a real life example. Think of Uber or Bolt. Every Uber driver or user can be seen as a node. The drivers are nodes, the users are nodes, and the application is trying to optimize so that the waiting time for each rider is as short as possible, right? So the algorithm is finding the connection between each node, that is each driver or each user, trying to like just check which connection is the shortest, has the shortest distance. Another real life example is Google Maps. Google Maps use graphs to find the shortest route between two locations. So final thoughts on choosing the right data structure. This is not ultimate, but it can help to make fast decisions. If you need to find something fast, you need a fast lookup, use an hash table. If you need ordered data, you want to store ordered data, use an array. If you want flexibility with your ordered data, use a linked list. If you need the last in first out principle, use a stack. If you need to use the first in first out principle, use a queue. If you will need some form of hierarchy with your data, then use a tree. If you need to establish relationships, network of relationships between things, use a graph. There's so much more to each data structure though. Each data structure has its own strengths and weaknesses, and the choice of which data structure to use depends solely on the problem you're trying to solve, the data you are trying to save, how you intend to use that data in the future. All right, thank you for staying to the end. I hope you learned one or two things from this video. If you enjoyed this video, please don't forget to give it a thumbs up. Don't forget to subscribe. Don't forget to turn on notification for more tech and coding content. See you in my next video. Bye.